Hello and welcome, space lovers, to our Winter Solstice virtual star party. Along with EV Scope users and space lovers from all across the globe, we are getting ready to take you on yet another cosmic tour, this time through the nebulae of the Milky Way. Nebulae are among the most majestic objects of the cosmos. They're vast, spectacular clouds of dust and gas, often where stars have died or are forming. Most nebulae visible to us are in our own Milky Way galaxy, the beautiful building blocks for stars, planets, and other planetary system objects. So we're going to travel beyond what is visible to the human eye to discover the colorful nebulae of the Milky Way. So once again, if you joined us earlier, you'll know Dan Peluso, PhD student with the University of Southern Queensland and researcher with our very own SETI Institute, scientific partner for those of us who work at Unistellar. His research involves finding and characterizing exoplanets, as well as improving science and astronomy education across the planet. So welcome back, Dan.
Thanks. Hello.
We're also joined by Val Clavins, Unistellar brand ambassador at the SETI Institute, who has a pretty cool history with Saturn, which I'm going to force her to tell us about later on when we speak to this incredible, great conjunction between two of our favorite planets in our solar system. She is also an expert in planetary astronomy, so she's going to be showing us some nebulae that were observed and captured by EV Scope users around the world and telling us more about these fascinating objects. So to start, let's watch a video and enjoy a bit about the nebulae of our beautiful Milky Way. All right, that was beautiful. Dan, can you tell us, now that we've seen these majestic objects, what is a nebula? Define it for us.
So a nebula comes from it's a Latin word, and it means cloud. And they're basically clouds of gas or dust in space. And stars, like our very own star, the sun, are formed in these nebula, or nebulae for the plural version. And what happens is when some stars die, they blow off their outer shell of gas and dust. And this wind of that shell of gas and dust being blown out can be lit up by the remaining core white dwarf star. And these are actually called planetary nebula. Our sun will actually do this in its very distant future. It will become a beautiful planetary nebula in many billions of years from now. High mass stars, so stars much larger than our sun, they live fast and they die young. And they're some of the most violent events in the universe when they die, because they explode in these events called supernova. And these supernova are so explosive and violent that they sometimes outshine entire galaxies. And they vaporize themselves in this violent expanding cloud of gas. And what happens is they leave behind these interstellar clouds, and they are lit up by other stars. And there's a couple different kinds of nebulae. There are nebulae that are called emission nebula. So they actually glow due to their own light. What happens, a nearby star will have light interact with it, and then the gas inside gets excited, and the electrons will jump up and down. And then when they jump up and down those energy levels, they'll emit light. And the different colors that you see, all the pretty colors of these nebulae, all tells us what is inside of the clouds, what kind of elements are in there. For example, hydrogen is typically red, oxygen is usually green or blue. Other elements might produce different colors. And you can even see these gases emit different energies in different parts of the electromagnetic spectrum, such as in the infrared or ultraviolet. There's also reflection nebulae, and these glow due to just reflecting light, hence the name.
And so I'm curious, why do some of these nebula look so colorful? And yet, if you were to use a traditional telescope, you don't really see much of the color. What is the difference between these images and what you can see with the human eye?
So with the human eyes, we see colors through these rods that are inside of our eyes. And at very low brightness, we don't see color. And since these objects are so distant and far away, we need to collect more light. And a telescope, such as the Unistellar UV scope, can collect enough light so that we can see those colors.
So could you tell us a little bit, the Hubble telescope, it's based out in space. Does that give it just this extra ability to capture images like this?
Yes, so the atmosphere is an astronomer's worst enemy when it comes to observing, because we get a lot of our light pollution, which in our cities can cause us to not be able to see the stars as we could in a darker area away from city lights. But also the gases in the atmosphere can help distract from what you're able to see. So the best place to have a telescope is in space, where you don't have to deal with the atmosphere and the problems of city lights. And the Hubble Space Telescope is an amazing instrument that is about the size of a school bus, and it has produced, I think, most of these images that we're looking at. And one of them that's really exciting, I think, which I think this image is a part of it, is part of the Orion Nebula complex and the Orion Nebula. And something, that's the horse head right there. But inside the Orion Nebula, the Hubble Space Telescope actually found, this is actually a really exciting thing. The Orion Nebula is like the star forming factory that's 20 light years across, and it's lit by 4 main stars called the trapezium. And the Hubble found that inside this nebula are protoplanetary disks. These are baby solar systems that we see forming. So we actually see solar systems forming in their infancy in one of these nebula. So these star factories, these are like literally like the creators of stars and planets, and we know at least on one of those planets here, life. So it's a very exciting thing when you look at these nebula, because you're really looking at the circle of life in the universe. I think you might be muted there.
Thank you so much.
No problem.
So Val, who's rejoined us, curated a series of nebula images captured by EV users from around the world. So Val, can you tell us a little bit about what we're looking at and some interesting facts about the Helix Nebula?
Yeah, sure. So here's the colorful Helix Nebula imaged by Tateki Goto from Japan. It's 650 light years away, which makes it actually the closest nebula to us. It's a planetary nebula, meaning that it formed from a dying star as it ejected its outer layers. And those outer layers, which are made of gas, expand and form the shape of that nebula. And just in case you're wondering, planetary nebulae have nothing to do with planets. In the center of the Helix Nebula is actually a white dwarf star, which is the remnant core of the star that formed the nebula itself. The star was actually a star probably much like our own. And in about 5 billion years, when our sun reaches its final life stages, it will also form a planetary nebula, and it'll leave a white dwarf in its place. So here's a Horsehead Nebula. It's one of my favorite nebulae, that's for sure. It's located about 1,500 light years away in the constellation Orion, which Dan was talking to us about a little bit earlier. So the Horsehead Nebula is a dark nebula. It's a dark tower-like structure of gas and dust where stars are being born. And the only reason why you can actually see the Horsehead is because it's situated in front of a reddish nebula called IC 434. So it's located within that Orion molecular cloud complex that Dan was talking about. And it's one of the most active regions of star formation in our night sky. It spans hundreds of light years across. So here's the Crab Nebula. It's about 6,500 light years away in the constellation Taurus. In 1054, a supernova occurred that was bright enough to be observed during the day, and it turns out that the Crab Nebula was formed from the supernova. That supernova not only formed a nebula, but also left behind a pulsar, which is a special type of neutron star that spins about 30 times per second. The Crab pulsar is an extremely compact star. It's only 12 miles across, so it's really small in terms of astronomical sizes. Yeah, so this next one is the Running Man Nebula. It's one of my favorites in Orion. It's located about 1,500 light years away, and it's one of the most well-known stellar nurseries in our galaxy. The blue color of this nebula comes from the reflected light of young blue stars. And the main star responsible is called 45 Orionis. It's seen sort of in the center of the image. And it's a bright blue star located about 900 light years away. And this nebula is interesting because it's made of a bunch of nebulae as well as an open star cluster. So here's the Iris Nebula. It's located about 1,300 light years away. It's a reflection nebula, which means that it scatters light from a nearby star. And in the center, you'll see a really bright star, which is that star. It's very young and has 10 times the mass of our sun. It's known as HD 200775. Another thing that's really interesting about this nebula is it's home to aromatic hydrocarbons, PAHs. which are complex organic molecules that make up about 10% of all the carbon in our universe. They also may be precursors to ingredients that sparked life on Earth. Here's the Omega Nebula. So it's a bit farther away, 5,000 light years away and 15 light years across. So it's a bit bigger than most of the other nebulae we've been looking at so far. It's a vast stellar nursery, home to about 800 stars, and there are more than 1,000 stars being born in its outer regions. The reddish color from this nebula comes from hot hydrogen gas from those infant stars. It's also known as the Swan or Horseshoe Nebula. The names Omega and Horseshoe actually come from John Herschel, who's one of the first people to make an attempt to accurately sketch the nebula in 1833. So this is a really cool nebula, the Western Veil Nebula. You might also know it as the Witch's Broom Nebula. It's actually part of the larger Veil Nebula, which is about 2,400 light years away in the constellation Cygnus. The entire Veil Nebula stretches out 130 light years across, and it covers the same distance as 6 full moons in our night sky. So about 10,000 years ago, a star 20 times the mass of our sun went supernova and formed this really large nebula. If you could see this nebula up close, individual parts of the nebula would appear to be string-like filaments, and each of those filaments are about 4 billion miles thick, which is about the same distance from Earth to Pluto. I really like this nebula. It's about 5,000 light years away and spans about 40 light years across. It's actually made of 3 different types of nebulae, as well as an open star cluster. That bottom reddish portion is an emission nebula. The upper, smaller, bluer portion is a reflection nebula. And the darker regions that appear to be gaps within the reddish part of the nebula are actually dark. It's actually a dark nebula. And so the word TRIFID, which is the name of the nebula, literally means divided into 3 sections or lobes. So that's where you get the 3 nebulae. And I think we saw images of this a little bit earlier from Hubble. I'll get into that a little bit later. This one's about 7,000 light years away in the inner spiral arm of our Milky Way, called the Carina-Sagittarius arm. So the Eagle Nebula is a diffuse emission nebula, a vast stellar nursery that doesn't have well-defined boundaries. So in the center, you might see 3 pillars of coming out in the center, and those are called the pillars of creation, which you may have heard of before, and we saw an up-close view earlier from Hubble. So each of those pillars are actually about 4 light years high, and the gas and dust within those pillars are creating new stars, while light from infant stars are at the same time eroding those pillars. So in some time, they'll probably change shape. Now here's the Bubble Nebula. It's a very different kind of nebula from the ones we've seen so far. It's about 7,100 light years away in the constellation Cassiopeia. It stretches about 8 light years across, which is almost double the distance from Earth to Alpha Centauri, which is the closest planetary system to ours. The Bubble Nebula is an H2 region emission nebula, which means that it's a region of gas and dust where stars are being born. The star that creates the Bubble Nebula is actually an extremely hot and luminous and short-lived star. It's about 15 times larger than our sun and 400 times more luminous than our sun. In about 10 to 20 million years, the Bubble Nebula will pop when the star goes supernova.
Sorry for the delay, trying to add myself back to the stream. Well, Val and Dan, thank you so much. I really appreciate you guys joining us, telling us a bit about these beautiful, amazing objects. Unfortunately, we're having some difficulty with our comments, so we were hoping to accept some questions from the viewers, but tech difficulties foil us, so I apologize for that. Val will be back in a little while to take us through some interesting observations tied to the Jupiter-Saturn Great Conjunction. So we'll see you again soon, Val. And Dan, thank you so much for joining us. And before Dan leaves, I just want to encourage everybody to seek out Dan's GoFundMe, which is helping to bring these powerful EV-scope telescopes to teachers around the world who so need these powerful teaching devices, but it also will allow these students to be connected to the scientists at SETI and other astronomers around the world. So please find the Powerful Telescopes for Teachers Around the World GoFundMe. You can find information at our unistellaroptics.com website, and later on we'll make sure that that link goes into the chat.
Thank you.
Thanks, everybody.
Thanks, everyone.
And I'm also joined now by Jim. So welcome, Jim. Thank you so much for joining us.
Hi, Whitney.
Hi. Dr. Jim Schweitzer is going to be sharing about our cosmic origins in the winter solstice night sky, because that's what it is tonight. It's this amazing opportunity for us not only to observe this conjunction, but also coincidentally to savor the winter solstice. Dr. Jim Schweitzer has a PhD in astrophysics. He's live here from the US, and he is one of the world's best experts on planetariums. So that is incredibly cool. He's a formidable outer space storyteller. Jim is also the owner and principal of Science Communications Consulting, SEC. And thank you so much. Welcome, Jim. I actually have some questions because your background is truly fascinating. Could you tell our viewers a little bit about what you do, your background, and the work that you do today?
Right. My background, I'm a card-carrying astrophysicist. Okay, so I have a PhD in radio astronomy from the University of Chicago. I spent my whole career, except for one part, I spent most of my career working on planetariums and the sort of educational programs that happen in planetariums. And I work on building large planetariums. I'll show you a picture of one in a little bit. But I also worked on radio astronomy observatory at the South Pole. But I've always lived in big cities. I've either lived in Chicago or New York City and worked in San Francisco a little bit. And so I've been a little bit blind from the night sky. So I've become a bit of an amateur astronomer in the past year. It's been great.
So can you tell us, why are planetariums so important? I mean, I can speak from my own personal experience of remembering planetariums as a child and just the incredible experience of being transported to distant places. And ever since then, I've sought out different planetariums. I'm curious to hear from you, who works in this industry. Why is it important that we keep planetariums alive and continue to invest in planetariums?
Right. Well, I'm glad to hear that made an impression on you. Which one was that?
So I actually remember going to the Air and Space Museum in Washington, D.C., and just feeling like I never knew that there was a world as majestic as this beyond our own Earth.
Right. No, that's great. That's a terrific place. In fact, I'm actually helping them renovate that. It's being renovated right now. I think planetariums are special because they serve many, many people, millions and millions of people every year. And they have consistent dark skies. So for me, I've been a radio astronomer living on where the dark sky doesn't even really matter. I lived in big cities where it's often been generally light polluted, unless there's a power blackout. In planetariums, it's always dark, right? I know one time I went to the West Texas Star Party and looked at the stars, and so it's just like the planetarium back home. So, it's not really, but planetariums are where we can learn about the deep universe, and they're very powerful. I've seen a lot of changes in them, including the revolution in digital planetariums. So we can not only just observe the night sky, we can actually go to the planetarium. So I urge people to all go visit the planetarium when they reopen again. It's been pretty tough for them during this last COVID year.
So, what advice do you have for people who are just getting started in astronomy and may feel captivated by what they see from us today? How can they learn more?
Right. Well, it's just such a fabulous subject. I've been doing it all my whole life. I'm always excited about it. To ask my wife, she sometimes thinks I'm too excited about it. But I think just find something that makes you joyful about it. I think it's the most important thing. I think, okay, I don't know all the audience here, but some may be children or younger people who are thinking about careers and this sort of thing. And remember that in space science, the careers they don't have to exactly be the science. But I had a student who was one of the colleges I worked with. Actually, she discovered a cave on Mars during one of my classes using Mars data, and then is now working for NASA in Houston in their communications department. So there's just a lot of interesting things, and most of all, just find something you really like. Now, for those who really want to be practicing astronomers like Dan and Frank and Val, you need to do your math, to take your math courses, learn a lot of physics, because it's all based on physics. And there's just so many wonderful opportunities for people too. These citizen science programs are wonderful. We didn't have them several years ago. People can participate at all levels. To be an amateur now in astronomy, it's like got to be the best time to do it, because there's just so many opportunities and tools. There's a lot of online stuff. I encourage people to look at, you can get the data from Mars and look down at a resolution of about 10 centimeters on a Martian surface. So there's just so many wonderful opportunities. And personally, I have to say, in this lockdown era, I know Mark Merrifield talked about it earlier, I got my EV scope when this happened. I was still teaching an online course, but I've had a great time in my backyard, and I live in Chicago. It's borderline sky. I'm right on the west side of Chicago, so you'll get to see some of the things. I'll take you on a little stargazing trip here in a minute.
I love that. In fact, are we ready to get started on our stargazing journey?
Yeah, I am. It's cloudy out tonight, so I have a backup version of being inside. Of course, it's pretty cold here. I can't complain too much about the cold anyway. So should I screen share?
Yeah, that would be great. That sounds good. And so our presentation tonight, we come from outer space, observing our cosmic origins in the winter solstice night sky. Thank you so much, Jim Schweitzer, for preparing. Just one moment.
Tell me when you're ready.
All right, go right ahead. Take it away, Jim.
Okay, thanks, Whitney. And hi, everybody. So, anyway, this screen has a little bit about me in the talk tonight, but let's just get started. I don't waste too much time. So this picture is, I want to tell you just a little bit more about myself, a little bit more about my background. I'm basically a Chicagoan. I live not downtown. This is actually shot from the regular planetarium, but I live just on the west side of the city in Oak Park, Illinois. I trained at the University of Chicago in radio astronomy. So in the center of this picture at the top is typical of a type of telescope I would have used in my youth. This is the NRAO telescope on Kitt Peak in Arizona. And you know, there we worry about dark skies. We don't worry about light pollution too much because we observe 24/7. You do radio astronomy, you basically have to figure out how you're going to manage to keep going out sleep or with shifts of other people. It's a very different system. But after graduate school, I went into planetariums and worked on the one in Athens for a number of years. The one in New York City, which is you'll see in the upper right, this is my project to oversee the construction of this, all the exhibits on planet Earth and their new digital planetariums. It was wonderful. And I still stay in touch with them and like them very much. I had a period of time, too, where I went back to the University of Chicago and helped manage and direct the creation of the observatory at South Pole. So that's where I am on the left. So when people say you can hear me complain about the cold because I've been used to it. Again, at South Pole, when I was there, it was light all the time. We built telescopes to look at the cosmic microwave background, basically. And so, you know, dark sky astronomy has just never, ever been in my life, if you will, until now, actually. I tried as a kid, but had the luck to do it. And so I'll show you some of my things in a couple of minutes. Let me show you a project I'm working on now because I know some people are interested in it. And I've been working on the Shanghai Astronomy Museum. It's my largest, in fact, it is the largest planetarium in the world. Shanghai has 27 million people, as many people there are in Australia. So they have the need for a very large planetarium. This is under construction now. This is actually an older construction photo. I was the science designer on the design team for the inside interior of this planetarium. Let me show you a couple of pictures of it. To call it a planetarium, it's actually it's a whole museum. There's a planetarium in that sphere, big digital planetarium. This is what it's like inside. It's really extraordinary architecture. The same architect that worked on the Rose Center in New York as well. But you have much more than that. There are exhibits on 3 floors. The entire facility has, it's like 58,000 square meters is the whole plot of land. And under the roof, there's 38,000 square meters. This is by far the largest astronomy. It's complete. There they are, actually putting the moon to place down in the lower right, exhibits on physics and scales of the universe. This one big picture is about a whole gallery on black holes, gravitation. So if you get to China, in a little over a year, this will be open. Oops, go back, sorry. Go back one more slide, sorry. I want you to see this from space. One second here. Okay, I guess you can see. So this is an aerial view of the new museum, and you can see how it looks from overhead. Quite elaborate. There are actually a couple observing decks, one over to the left and one to the right. The one on the right, the little one that looks like a donut, will actually be a place for children to observe from a children's camp where the children can actually stay overnight. It's really extraordinary. One of the exhibits I worked on, though, I want to tell you just a little bit more about here, and that is they wanted to recreate Galileo's life, in a sense, and the whole gallery on Galileo, and create a room where Galileo might have had discussions about astronomy with people. So I was lucky enough to get to really dig down and bore into Galileo. And, Galileo is where it all started for us, especially when people were interested in telescopes. In fact, looking up on January, but in January 1610, he observed, just like people are today, looking at Jupiter and Saturn. He didn't see Saturn then, but he was looking at Jupiter, and he saw the moons, named for him the Galilean moons. This is his notes that he did on another letter of the moons of Jupiter. So we can connect back to that time very easily. But I think we also need to remember how, when Galileo did this, especially the observations of Jupiter, he really ushered in the scientific revolution by proving the Copernican theory. The picture on the left here is Copernicus' model of the solar system with the sun at the center. This is the origin of the word revolution, comes from this. It was Galileo with his telescope. Here's a picture of the Museo Galileo in Florence, looking through a replica Galilean telescope with the curator, Dr. Strano there, doing research for this. And it's really just important when we talk about telescopes and use telescopes to remember how important they are. The invention of the telescope really, it just changed our view forever of an understanding of ourselves and our place in the universe. And it ushered in the scientific revolution. So before I get to the sky, I'm giving you a little more of this background. I also want to prepare you for another part of a scientific revolution that kind of happened in the 20th century. And that is nuclear physics. I'm happy to be a University of Chicago graduate where a lot of this happened. When we discovered that atoms had nuclei, and the nuclei reacted one against another, they ushered in this era of nuclear physics. And we used it, of course, in astrophysics to understand how stars get energy. So 4 hydrogens make a helium in the sun where the temperatures and pressures are hot enough to do it. And that's the source of the energy that's coming out the sun and heating our planet and so on. So this nuclear revolution was, in some ways, as important scientifically as the telescope, and it also lets us to understand the evolution of the elements, because in fact the elements are all the elements heavier than hydrogen and helium. Helium and hydrogen come from the Big Bang for the most part, but extra helium and heavier elements yet come from nuclear furnaces within stars. Okay, we're going to do some stargazing now, but I have one last thing I want to just make sure is clear before we get going, and that is the sorts of nebulas we're going to talk about, or nebulae. The use of the word nebulae has changed a lot over the years. And Messier, you've heard already about Messier, he had a catalog of nebulae and star clusters. If you look at the whole Messier catalog, you'll see that half of it are star clusters. So open and globular star clusters, we'll look at a couple of those tonight. I'm not going to talk about galaxies. Mike talked about that earlier. If you didn't see that, go back and watch his video. It's excellent. I'm going to talk more about this 11% left. These are ionized clouds of interstellar matter, okay? And then there's a 3% of some odd ones. But the ionized clouds are the ones we're going to talk about. And so just fill you in those one moment as well. Galaxies, like the ones Mike talked to you about, are made up of stars, much like our sun. And stars light across the spectrum continuously, right? And that causes, when it's all blended together, it becomes white light. In fact, in the old days, galaxies were called white nebulae. Before they were sure they were made out of stars, they would have called them white nebulae in the old days. Now, nebulae like the Orion Nebula, which is the poster child for all of these we're going to be seeing, emits in these particular colors, very precise, like tones on a piano, a red, oxygen green, some other, and hydrogen. These are the main spectrum lines that are emitted, and you can see them. Now, to our eyes are not real sensitive to the red as much as they are to the green, so that when you look through a normal telescope, you're going to see these nebulae I'm going to talk about tonight as the green ones. So there's a time when they talked about white and green nebulae. And tonight, we're going to focus a little bit more on these than, well, we're not even going to look at galaxies tonight, except our own. So here I am with my telescope back when it was warm in the summer in my backyard. If I could take you out tonight and it was warm and clear and we could all go there, this is where we go. It's about a mile away from my house. This is a baseball park. It's called Lindbergh Field. And we would go past our field and set up an EV scope. It's a pretty good place around here, even though this is a relatively close-in urban environment. The skies can be pretty good, not on the night of this. The pictures I'm going to show you tonight and the observing I'm going to take you through tonight were done, though, all in my backyard. This is what it's like in my backyard. Mike showed his. I enjoyed seeing his. But I did almost, I think all these pictures were taken in this environment near my garage in the alley, and I shoot between these wires. So whatever you do, don't worry about wires and things like that. You can make it happen. I've been really surprised. But let's go back. Imagine you're out of this field. Let's go back out to the field. I'm going to draw you a sketch to show you what the sky would look like just now. If we could go out, if we face south, so you're seeing, I'm a planetarium guy, right? So this is like half a planetarium. We're looking south. If you turn a little bit to the left, that's the east. A little bit to, 90 degrees to the right, and it's the west. And then the Milky Way, if you could see it, you can't really in our skies, but it's there. It just streams across the sky overhead. So this is the sky we're going to look at tonight. And there's Mars would be up. It's in the center here, and we have a nice first quarter moon as well. I can't see it tonight. It's unclear, but I can show you. We can do this sort of virtual star trip. So we're going to look at all these 6 objects that are in red. And we're going to look at them one by one to try to learn some things about them. All these images I took over the last year, you'll see the dates on them as well. The first thing we're going to look at is M15, Messier 15. It's the constellation Pegasus. So what is this? I like to prepare people for what they're going to see first with just like a cartoon. It's a globular cluster. It's like a lot of stars, man. I mean, there's 100,000 stars here. and it's pretty much spherical, and they're self-gravitating. They're all old stars. So think about, old guys and old women. Okay, it's like an old people's home of stars. Here's the image I got in July, about 5 minutes from here. Again, it's a globular star cluster. It's like 33,000 light years away. If you're an EV scope user, hold up your hand. I can't, but I'll give you a trick I've learned. That the field of view of the EV scope, if you take that field of view, it spans the distance to the object divided by 132. So 132 is a magic number. Just take the distance. You have to look this up. Divide by 132, it gives you an idea of what your field of view is. Okay, so this thing is a couple hundred light years across. The important thing here is that it's 12 billion years old. These are the old stars we know and can see. So when we're looking at this, we're looking into an old people's home, basically. Our galaxy has many of these clusters running around it. They're leftovers from the time when our galaxy was put together, basically. And they contain the oldest stars, and they're made primarily hydrogen and helium. I mean, they've been fusing some heavier elements, but if you did a spectrum of these stars, you would see very few elements heavier than helium, 1% of what we know. So the next thing I like to do in my little observing programs is then now connect you with what you're going to see online often. And that is, you're going to go look at Hubble images. They're wonderful, or some real high-end things. The telescopes cost $1 billion. Here's M15 seen by the Hubble. But I want to emphasize that a lot of the Hubble images, look at them carefully. They're gorgeous, stunning, but they're often false color. So this one of M15 shows you many more stars in greater detail. It's really a montage of ultraviolet, infrared, and optical. So they've combined invisible wavelength bands on the red and the violet side of the spectrum to make this image. This is typical of these sorts of things. All right, go back to the sky. Right? So, and what's amazing I've found, like with my scope, is that if I get set up and have my observations planned right, I think I could have actually gone through all of this in an hour without too much trouble. I'm talking a little bit and explaining a lot now. I might not do so much as we run outside. So the next object let's look at is M27, Messier 27. Right about now, it's just starting to set. Would be a little hard to, unless you could see down in the west. It is a planetary nebula, which the name comes from. They used to look like planets, so they look like planets in a small telescope if you don't have much magnification on them. What they really are is they're a dying star that's ejecting its outer layers, typically a light or less in diameter. And that gas is ionized, and that's what causes it to glow in those spectrum lines I showed you before. It's very hot dying stars. Sometimes they're evolved all the way to white dwarfs. They're not always white dwarfs, but are on the way to becoming white dwarfs. Occasionally, they're butterfly shaped. They come in all kinds of shapes. Tonight is one of the pretty stars of. If you have an EV scope, you haven't seen Dumbbell Nebula. Well, you haven't lived yet. It's probably one of the most amazing ones to look at. You can, if you look carefully, you can see a little tiny bluish dot in the center. That's the star, which all these gases have come out, these ionized gases. It's about 1,200 light years away. It's only 15,000 years old. It's really, really quite young. The colors of those gases, the green, if you remember, that's going to be mostly oxygen. That is oxygen being heated up. It's actually doubly ionized oxygen. And then the reddish color are principally hydrogen, but a little bit of nitrogen too. So this star is the source. The stars like this, if you find oxygen, nitrogen floating around in outer space, in interstellar space, that came from stars like this, how it gets back to the stars now. Now, I was experimented earlier this year, back in September. I actually got a filter that just filters out the oxygen light, and I put it on the telescope and tried it out, and this is what I got after 4 minutes. So you can see, if you have a real narrow band filter, you can pick out just one element if you like. Now, if we were to look at this Hubble, this is a Hubble picture I got of M27 close up, you see something a little bit different. The Hubble sees extraordinarily fine detail. So they're actually seeing little clouds and clumps and lumps in it. It's really pretty amazing. But one of the points I want to make is that the EV scope's field of view, which is about a half degree, is about 90 times wider than Hubble's field of view. A lot of people don't know that the Hubble is real pinprick precise in its high resolution. So it's like a super uber telephoto that only sees a very tiny point of view. So I couldn't even find an M27 taken by Hubble because it's just too big. So remember that the Hubble is doing very, 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 very precise things. Go back to the sky, and we're gonna go from west to east on this. So we've seen old stars with hydrogen. We've seen M27 showing us a lot of nitrogen and oxygen coming out. I want to go to another really important element in my story tonight, and we're going to find that here. We need to go to a star to do this. And I want to emphasize too, if you're a EV scope user out there, look at stars. There's a lot of interesting to look at nebulae. They're beautiful and spectacular and big, but the stars are really interesting to look at too. So we're going to look at T Lyrae. It's the name of the star. It's right near the ring nebula axis, not too far from it. It's what's called a carbon star, and I think even Mike talked about this. Someone talked earlier. There are stars. The cartoon of Winston Churchill, but think of him smoking his cigars and all that soot and smoke and junk coming out. That's what these stars are like. They're the smokers of the world. They eject shells of soot and dust and organic molecules into space. Let's take a look. This is a picture I took back in May, actually. I just have coordinates of the star. I don't have names on it, but it's T Lyrae. It is called a carbon star. And we know of hundreds of these. This one's about 2,000 light years away. And it's only 700 million years old. And it's the source of carbon in the universe. These stars basically fuse helium into carbon and put most back out into space. So any carbon that's floating around gets recycled into stars or planets or life has come from the sort of past. This was in your past. Now the Hubble, there's only a couple carbon stars that have actually gotten some size to them. Even giant stars like a carbon star don't yield sizes easily with optical telescopes at all. So it turns out with radio telescope, you can actually image them a little better. I'm going to show you a radio picture made by the Very Large Array out in New Mexico of IRC 10216, it's actually the brightest infrared source in the sky, infrared star in the sky, and we can hardly see it, although I'm going to go look for it with my EV scope. I think I can catch it a little bit in the visible. Well, with the Very Large Array, we can combine the radio telescope's data to create images. And in this case, we actually see the shells, the material. It's all kinds of chemicals and schmutz and all kinds of junk coming out of this thing. It's a real pig pen of stars out there, but it's a good one because we need the element for a lot of the things we know. Anyways, let's keep going. I don't want to keep this too long. Let's see. So we've gone to the west, right? We're going over to the east. We're at 3 more objects, and they're Messier objects. It's just a little. They're nice and bright. It's really a wonderful time to be outside. So we'll go to M1. I love it. It's the first one, Messier 1. It is a supernova remnant. That's just what this thing is. It's basically it's a nebula where we'll see the envelope of a star blasting off from a star explosion. These star explosions, like the ones that made this nebula, are the sources of the heaviest elements, because when you have the star explosion, you can have even more intense energies put into these nuclei at higher temperatures, higher densities. And you can form all the rest of the elements through iron, gold, you name it. Incidentally, we know that neutron stars can collide and form heavy elements too. We didn't know that story except just the last decade or so, last few years. But now we still know that places like M1 we're just seeing the outpourings of a big fusion event in its outer layers. This picture I love because I actually think this is the first picture I took with my EV scope. I took it outside last February, and I said, what should I go? Well, let's go M1, the first one. So that's what I went. It's like Marx Brothers joke, what's the first number? 1. And so here was my first picture. Again, it's a supernova remnant, 6,200 light away. You know its exact age, it's 966 years old because Chinese and Japanese astronomers saw its explosion go off in 1054 AD. And if we analyzed it more carefully, I want to show you. I went out just the other night in preparation for this, took another picture. This time I went 14 minutes. I'm very proud of this picture because it's just much better than my first picture. Even though I was excited with the first one, this is much better. I'll be honest, I tweaked this a little bit in Lightroom to bring the colors out just a little bit, but and I have to say that software has improved dramatically just in the last year as well. So it was the Crab Nebula M1. This is a source of heavy elements. And when we're talking about ourselves and things like that, we think of iron in your blood, calcium in your bones, or phosphorus used in ATP, the energy that powers living cells. So we have a past with these things, even though we were talking earlier about how can you get your head around them being so far away. Well, the stuff just isn't that far away. It's all in us. A Hubble picture, they did do a huge mosaic of Hubble, of the Crab Nebula, because it's just so incredibly important astrophysical object. And so lots and lots of images went into putting this one together. And you can see all this incredible structure of the explosion. But I also want to mention one more time to be with fall colors. They used 3 different filters in making this image. In fact, the Hubble red is really green in real life. The Hubble green is really red in real life, and the Hubble blue is really orange in real life. So there's if you want to interpret it correctly, don't always interpret it as being what you would literally see. It's colors have been rendered this way to help us understand this, and that's what science does. It's mostly about helping us understand these things. So after looking at all these different objects, we realize in these nebulae, we're seeing the elements that go into life. This is where the title of this talk came from. We come from outer space. So literally, humans, life as we know it, couldn't exist early in the universe. Probably not so that. I guess Frank's going to talk later, but when we go back to M15, I'm not sure there's going to be too much advanced life because I don't know if there could have been a generation of stars they benefit from the processing of the earlier generation. If you were to look at the numbers in terms of the primary elements in the human body, this is how they go out by weight. 65% is oxygen. This is from water because we're mostly made of water, at least in terms of weight. 10% hydrogen, which is to go with the water. We're about almost 20% carbon. Because all the carbon molecules that go into proteins and fats and nucleic acids and other sorts of chemicals. There's like 100,000 different types of carbon molecules in us. Nitrogen, which is of course in the proteins, amino acids, and so on. Anyway, so those nebulae also talked about origins. Let's just hit 2 more things as we go on. I want to close the loop on this whole story. And the closing the loop is to go to the next generation, the future generation from us. Best place to look at this happening right now is to look at M42, which is, of course, the Great Orion Nebula. It's hard to interpret that nebula. When I worked at the Rose Center at Earth and Space, we worked on a show where we actually modeled it in 3D and flew through it in the San Diego supercomputer. But this is my sketch of it. We're going to look at it from the side. If you look at the nebula from the side, you've got this fan shape of ionized gas sort of coming up from us here. There's a cluster of hot stars in the middle called the trapezium, which is these are hot young stars emitting out of ultraviolet light, cause the ionized gases to glow, and especially hydrogen light, and also oxygen light. There's a bar sort of across the nebulous edge of the huge molecular cloud that's there. Of course, this one is got to be the first thing. If you get an EV scope around now, first thing you really want to look at, because it's just spectacular. It's the easiest thing. And there's about 2,800 newborn stars in this area. It's not just the trapezium, they're lighting it up. And it's only 3 million years old. So astrophysically, this thing is a real, it's a nursery of stars, really. So these are the future generation, the new stars and their solar systems. They see new solar systems forming here from the recycled elements, the ones we saw. And there's a big thing going on here. I think Val did it this earlier. This is the Orion region. This is the whole region. They put this up so you get yourself as a constellation, you know, this sort of hourglass shape with the belt stars there. When you put your EV scope on M42, it's just looking at this much, not that much. But the whole region is sort of a fire with star formation. So what happens next in the story of these evolution of elements and stars and so on? So we're going to turn to our last, let me just say too, as a planetarian person, astronomy storyteller, what's amazing to me is I can go out and set this thing up and I could find half a dozen objects, probably any season, and tell an interesting story, I think. So it's not just, we're going to just look at Mars, or we're just going to look at the moon, which I love, but we can go much deeper and prolong story. So here's M35 as the next one in a while. Look at, and so this is one of these guys. This one's wonderful also because it fills the field of view so well. This is an open star cluster, about 3,000 light years away, but you'll notice it's very young compared to the globular cluster, which the globular cluster was 10 billion years old. This is only a little over 100 million years old. So this is like a new family, if you will, of stars that were born together. It will live together as a group like this maybe for another 100 million, maybe 200 million years, and they'll get pulled apart by the gravity of the galaxy. This is what the Orion Nebula area will look like in another 100 million years or so. So you're getting a preview of that. Anyways, those are the things I wanted to show you. Let's recap now quickly what we learned from each of them. I'm going to put each one of these guys up here. So yeah, remember M15, the Great Pegasus Globular. What element does that point us to? Well, it really tells the story of hydrogen, because it's made of, it is our connection with the primordial creation of the elements in the Big Bang, and hydrogen and helium. This is a place where there's lots of hydrogen, some helium, and it's fusing, but not much else. So those are old stars, I'm sorry. Then we saw the dumbbell, remember? And this is where we actually see the gas. We see oxygen and nitrogen being recycled back out into the galaxy. We saw the Crab Nebula, right? And the Crab Nebula is the source of an explosion that generates even heavier elements like iron, calcium, and phosphorus, all very, very important for life. And of course, our friend, the little carbon star, the little red guy here, he's in fact, it's probably the only real important source of carbon. And interesting thing too to understand about this, if you thought of this as like a real person with an 80-year lifespan, it burns its helium into carbon in a space of 8 days at the end of its life. So it's like Winston Churchill smoking up a storm at the end and ejecting most of it at the very end. And finally, the Orion Nebula, think of recycling when you look at it. I'm looking at matter being recycled. The actual glowing stuff is just stuff being burned off. The stars and the star clusters are all recycled elements from earlier generations. And then finally, when you these open clusters, think of youngsters or young stars, and you'll have the right picture. So that's basically the story I wanted to tell. I want to also acknowledge that this is the solstice, and we're having this amazing conjunction. I hope people have been able to see the conjunction. This was about a week ago. A friend of mine, Derek Demi, took this picture. And this morning I got to see Goto-san's amazing picture from Osaka with his EV scope showing the Jupiter and Saturn and the 4 moons of Jupiter, and also there's some interloping star, HD 19250 as well. So I think I'd just like to end by wishing everybody a really happy solstice. You know, solstice is a time of rebirth and hope. But when you think of our galaxy, with galaxy, it's factor. It's recycling star material, generating new stars at the rate of 7 new stars a day, I think. And with what's amazing is this technology, whether it's this telescope or the technologies we have access to, we can actually perceive this story. No other generation's really been able to do it easily. And all this science, this important science, came about a lot because of telescopes and the research people did. Even research maybe some of you will be, you know, really famous research astronomers in the future. I hope so. But it gives me a lot of hope because we really need to rely on science these days. So I hope that story made some sense to people. I'm very grateful to be here. I want to thank you very much for having me. Let me come out of here. Can you still hear me? Wait, I can't. Okay, I'm going to stop my screen. Sorry.
Hey, Whitney, you're mute.
Oh, I muted myself. So Val, welcome back. And we're so excited to check out the Jupiter-Saturn conjunction. And so I'm hoping that you can tell us a little bit more about this pretty incredible event. May or may not have been the Star of Bethlehem. Tell us a little bit more about why tonight is so special, and share some facts about Jupiter and Saturn while you're at it, if you don't mind.
Sure. So this is really exciting because it's such a rare alignment of Jupiter and Saturn with respect to Earth. To give you an idea of distances, currently Earth is about 500 million miles away from Jupiter, and Jupiter is another 500 million miles away from Saturn. The last time Saturn and Jupiter were this close in the sky was almost 400 years ago in 1623, but they weren't visible to the naked eye because it happened during the day. The last time they were this close and actually observable was about 800 years ago in 1226. So if you still have some light out there and you haven't seen the conjunction yet, about 45 minutes after sunset, look towards the southwest over the horizon. You should be able to see 2 bright objects in the sky, close together, that look like stars. Saturn is the dimmer of the 2, slightly above, and the brighter one below is Jupiter. So if you're using binoculars to see the conjunction, you should be able to make out Jupiter and Saturn pretty distinctly, as well as 4 of Jupiter's largest moons, which is the Galilean moons, called Ganymede, Callisto, Europa, and Io. And then you might be able to see Saturn's largest moon, Titan, as well. So I'll tell you some interesting facts about Jupiter. It's the largest planet in the solar system, if you didn't know that already. It's one of the brightest objects in our night sky after the moon and Venus. It's a gas giant planet, which means it contains mostly hydrogen and helium. It also has 79 known moons, the largest of which were the Galilean moons, which I mentioned earlier. It's also the fastest spinning planet in our solar system, and it takes about 10 hours to spin once around its axis. Jupiter's famous storm, which you can see right there, the Great Red Spot, is actually the largest storm in our solar system. And I'll tell you some facts about Saturn. It's the 2nd largest planet in our solar system, and like Jupiter, it's a gas giant planet containing mostly hydrogen and helium. So Saturn's rings are the most magnificent in our solar system. They're made mostly of ice particles, but also rocky debris and dust. Saturn also has a giant hexagon in its north pole. It's a persistent giant hexagonal jet stream. Saturn also has 82 known moons, some of which contain water, which may mean they have life. Saturn's largest moon, Titan, is really fascinating because of its thick atmosphere, rivers and seas of methane, complex hydrocarbons, plastics on its surface, and liquid water beneath its surface.
Val, could you tell us a little bit about the images that you actually created using data that was captured by the NASA Cassini mission?
Sure. So if you go onto NASA's website, there's raw images that this Cassini spacecraft took. They're in black and white, actually, and I composite them together to get the visible spectrum, the red, green, and blue images together, and so you could see an actual full color view of Saturn and its moons. And I did that for fun for a while, and then got involved in a space IMAX film called In Saturn's Rings. Quick plug for
that. Check out In Saturn's Rings. We also had you curating throughout the past few days and into today some of the best observations of the conjunction from EVscope users throughout the world. And I think for those of us who were not blessed by clear skies tonight, it'd be great to see what some others saw. So can you tell us a little bit about this first image that we're looking at, which is from, I believe, yesterday?
Sure. So in the image on the left, you can see a dim star and a brighter star, and the dim star is Saturn and below is Jupiter. And so the middle image shows you sort of where it's located within our night sky and some constellations. That bright yellow dot on the bottom is actually Jupiter and Saturn, and above that is the constellation Capricornus. And then the image on the right is a blow up. It looks like we're using an EVscope of Jupiter and Saturn. Saturn on the top, Jupiter on the bottom. And so here's a really cool image from Mark in France. You can see Jupiter and Saturn, but also some of their moons, and off to the right you can actually see a star as well. If you look closely, you can see a little bit of the bands of Jupiter and Saturn's rings as well. And so this is a really cool image. Lionel is actually located in the southern hemisphere in Reunion Island, which is an island off of Madagascar. And so you see a slightly different view of Saturn, Jupiter, and its moons. And so here you can also see Jupiter and Saturn and its moons again. Off to the right is Titan, actually, that dot over to the right. And you can notice that Jupiter's moons are all together in the line, which is the plane of Jupiter and its axis of rotation. And here's the image that Jim showed earlier from Tateki Goto. So a really nice view of Jupiter, its moons, and Saturn, and Titan, and even that star, if you can see there next to Io.
And you actually did an observation earlier, and so I think we can add that in so that people could see what you saw at the same time. Yeah, look at that.
Sure. So yeah, I just took this about an hour ago. I'm currently located in Sarasota, Florida, so we have some good weather, no clouds. And yeah, nice weather. So just in the center, you can see Jupiter, and Saturn off to the right, you can see Saturn's rings. And so I was changing the exposure and the brightness to get these images So now, as I changed those, you can see Jupiter's moons coming in. The top one is Callisto, and then Io below it, and then Ganymede is like right behind Jupiter, slightly above, so you can't really see it. And then below that is Europa. And then I changed the settings again, and I could see more moons and stars. And off to the right of Saturn is its largest moon, Titan.
All right. Well, we are also joined by someone else who's been doing an observation this evening. So hopefully at the end of our time, or maybe at the beginning, he'll have to tell us, we'll be able to do yet another observation. It is a colleague of Val's from the SETI Institute. Here he is, Frank Marchese. You may remember Frank from some of our previous Citizen Astronomy Month live streams. Frank is senior planetary astronomer at the SETI Institute and chief scientific officer at Unistellar. The SETI Institute is a nonprofit research organization that looks to understand life beyond Earth. And so we'll segue. Thank you so much, Val, for joining us for this portion of our presentation. Now we're going to transfer our time into something very, very serious. So my first question that I have for you is, let me add this here. It's very specific to the Galactic Federation. Anyone who joined earlier knows I'm very curious about this. So if you look up the news, you will see this is true. Senior government officials keep saying that UFOs and aliens are real, and now it's spread across the globe, and apparently there is a Galactic Federation. Is this true? What can you confirm or deny in regards to the Galactic Federation?
Hi, Whitney. I'm glad you're going straight to the point. No filter. Hi. So,
inquiring minds want to know.
I know people want to know, right? So, I'm a scientist at the SETI Institute. We are looking at the sky 24/7, and we basically search for life on the planet. So, I think we are the most ready to be contacted by the Galactic Federation. And I'm going to tell you that nobody at the SETI Institute have been contacted by the Galactic Federation. So I do not think that the Galactic Federation exists, or at least has contacted some people, some official in Israel or something like this, which is what I read recently in the news. So we are looking for life right now. We are spending time and money to look for life. I would love personally that this to find an answer to the question whether or not we are alone by finding the galactic civilization. That would be the best conclusion, and that would be an easy answer for me. But unfortunately, I cannot tell you that there is a Galactic Federation because we have never been contacted by them and we never seen them. Sorry.
So that seems like something that is a little bit easy to dismiss, but something that maybe was a little bit more provocative for people recently was news that there was a radio signal coming from our nearest stellar neighbor. Is this any more legitimate? What can you tell us about this radio signal?
Yeah, so this is an announcement which is based on a leak from scientists at the Breakthrough Listen. So that's coming from scientists. It's not coming from some official somewhere else. It's very interesting. In fact, there's a group of scientists funded by Yuri Milner called the Breakthrough Listen. They're using the Parkes telescope in Australia to listen to stars nearby. And some of the application of this listening is to find for so-called techno-signatures. Signatures coming from civilization like ours, which are emitting radiation to tell us that they're here. This is basically the SETI search that we started 35 years ago, but now they're using new technology, new computer, new data analysis to get more data and to listen to more stars. So the Parkes telescope is a gigantic telescope. It's the largest steerable antennas in the world in the southern hemisphere. And they pointed this telescope to our Proxima Centauri because Proxima is very close to us. It's only 4.2 light years away from us. The size of the galaxy in diameter is 200,000. So that gives you an idea. We are talking about something which is very, very close to us, like our neighbors. And they detected a signal. I forgot the frequency, so I'm not going to say the number, but it's a signal which is very sharp at one specific frequency and seems to be moving due to the Doppler effect. It's an interesting signal because that's something that they are looking for, a type of signal that will be artificial. We think it's artificial, but most people now are convinced that it's not coming from Proxima Centauri. It is coming from Earth or from a satellite in orbit around Earth. They are still working on identifying the satellite or the source, and we think that we will find pretty soon the source of interference. Once again, this is an unpublished result. It's based on the leak. So most of the thing I'm telling you right now will be probably wrong in the next 6 months when the paper will be out.
So even though these two things seem too good to be true, the work of the SETI Institute is very legitimate research focused on the search for extraterrestrial intelligence and life beyond our own known civilization. So can you tell me a little bit about SETI and the work that you guys have been doing?
Yeah, so the SETI Institute is a non-profit organization located in Mountain View, California. We have approximately 100 researchers working over there. Each of us are looking for life, any type of life, microbial life, intelligent life, technological life, somewhere in our galaxy. So those are the kind of the three main themes of the SETI Institute. First, if you want to understand if there is life or not in our galaxy or our universe, you need to understand our universe, our galaxy. So part of our scientists are cosmologists, astronomers who work as well on the international, the formation of galaxy, the evolution of galaxy, planetary systems. This is basically the first part of the search. Truly understand how a star evolve and form a planet, for instance. As you know, we are part of dust. We're made of dust, basically, dust of planets. So if you want to understand life and us, we need to understand where these materials come from. The second part of the search is the search for exoplanet, any type of life, a planet in orbit around another star. One of the main, one of the radical change, the paradigm shift we had over the past 4 years is that now we know that when we look at the star in our galaxy, we don't see stars, we see planetary systems. And this is due to the fact that each star has 2 planets in average in orbit around them. Among those 2 planets, among those planets, with 450 or 200 billion stars in our galaxy, so 400 billion planets, okay? And around this 400 billion planet, we think there is at least 300 million of them that could be habitable. So located in the colloidal zone of the star, where there is liquid water, and with a size which is close to the size of our own Earth. So that's a lot of words. That's a lot of words that could be habitable. I never say they're habitable because we don't have a picture of them. We have not seen all of them. For the moment, we have detected 4,000 exoplanets, and we have a picture of very few of them, like an handful number of them. But we are making progress, and the next step in science is to be able to take a picture and analyze the light coming from terrestrial planet in orbit on other stars. Because when we have a light, we have the color, we have the temperature, the composition of the atmosphere, and we will be then capable of inferring the presence of life on this planet. And then the third part is the study of intelligence itself. So this encompasses a lot of things. The study of language and intelligence on our own planet, for instance. We have a group of researchers who are working on understanding how whales communicate with dolphins, because those are intelligent species on our own planet. We know that chimpanzee can do math, for instance. So there is all of this intelligence that we did not see, we disregard for the past 1,000 years, and now we are realizing that we are surrounded by intelligent species. So it's great to look for those which are far away from us, but let's first understand our own intelligent species, our own biosphere. So that's one side. And then the second part is to look for this intelligence intelligence elsewhere. So for this, we have this array of antenna, the Allen Telescope Array, which will be capable of basically listening to the stars and detecting technosignatures that I mentioned previously in the case of the parks. This is an array of telescope that belong to the SETI Institute, managed by the SETI Institute. So we use it almost exclusively now for this kind of research. And there is another type of research for intelligence we are doing, which is what we call laser SETI, or SETI. So this is a new type of search, and that's the project led by Elliot Gillum, who is a researcher at the SETI Institute. The goal here is to put around Earth 8 spectroimager camera that will be basically looking at the sky 24/7. And they will be able to detect the presence of a pulse, a laser pulse. We anticipate that if a civilization knows that we are here, for instance, because they have detected our presence in our biosphere, they may want to communicate with us. They could communicate using radio emission, but they could also communicate using powerful lasers, which are have a better propagation and have a better can move at a very specific, send a lot of information at a very specific wavelength. We're using more and more lasers, so that's why we anticipate that an advanced civilization will also be able to do this kind of use as well this kind of technology. So this project is to basically look at the sky and detect those laser pulses. So what we are doing now at the SETI Institute is to collaborate with the Laser SETI project, and we want to be able to use the Unistellar network to follow up, to confirm the existence of those laser pulses. That's something that's going to happen in the next 2 years, probably, or even less. One of the stations is already working at the Robert Ferguson Observatory here in California. We're going to have another one in another part of the world. Follow SETI Institute to know exactly what happened with this project. So, sorry. You mute me, Whitney, again.
That dreaded mute button. So I'm curious. We've talked in a previous presentation about the Drake equation, and it comes up oftentimes when people are talking about the search for extraterrestrial intelligence and intelligent life. And it's really interesting because it has so much to do with all of the different types of research that you conduct at SETI and also the opportunities for us at the Unistellar Network. So could you tell us a little bit about, it seems complicated, but it really is fascinating. What is this equation that we're looking at? And can you briefly take us through these different parts?
Yeah. So it's not really an equation, because an equation is made to solve a problem with by understanding the relationship between parameters. Here is more like a way to quantify the number of technological civilization in our galaxy. We know that this number, which is called n, is the product of various parameters. So when you get hired at the SETI Institute, basically, one of the questions you have is how your research could help to refine one of the parameters of the Drake equation. When I joined the SETI Institute 10 years ago, even more, Frank Drake himself asked me this question. So I do remember that. So here, the parameters are the following. So the first one is very known now. It's the rate of formation of stars in our galaxy. And we know it's roughly 100. There is 100 stars formed per year in our own galaxy. This was known in the 80s, 90s. The second parameter is a fraction of those stars which have a planetary system. You remember I just said at the beginning of my talk that now we know in average each star in our galaxy has 2 planets. So this parameter is 1, basically. We know now that all stars almost in our galaxy has a planet. And then the second parameter is the number of those planets which are in the habitable zone of the star. And again, I just mentioned the number. It's 300 million stars. So it means that there is 30% of those stars, of those planets, which are 30% of those planets which are potentially habitable. That's a large number. And this is a new number. I mean, this paper was published, I will say, like a month ago. So we just basically, we think, nailed down this parameter. Of course, there is still discussion in the scientific community, but it will not move that much. I think it will stay always very high, between 10 and 30%. So now we're entering in the terra incognita of the equation. We don't know much about those parameters yet, but we are working on that. The one that we're trying to understand is FL, which is the number of those, the fraction of those planets suitable for life that will have life. So imagine now we create 200 different Earths, okay, located around the same star, etc. How many of those planets will have life? How many of those planets will develop life? We don't know. And the reason for which we don't know is because we have one system to study, is ours so far. We have found life only on our planet. When we will find life on Mars, on Enceladus, on other exoplanets, we will learn a bit more. We will basically be able to quantify this FL value. I'm very optimistic on this value. And the reason I'm very optimistic is because if you look at the evolution of our own planet, when our planet had life, had water, and our planet was basically still not potentially habitable, because there is a lot of radiation, a lot of asteroid impact, variation of temperature, we had bacteria already. So this means that life seems to come very quickly in a planet, as soon as there is liquid water. So I will say that this parameter is 1. And then we have to enter in like the very unknown part, which is what the fraction of those planets that will be intelligent, will have intelligent life. And that's difficult because once again, we don't have that many systems to study. We have our, and what the fraction of those intelligence that will basically develop technology. Intelligence is not always linked to technology. And an example again is the whales and the dolphins on our own planet. They seem to be intelligent. We don't really know yet at which level of intelligence they have, or the gorilla, but they seem to have social interaction. They recognize each other. We have taught a gorilla how to speak with sign language. So this means that they can speak. They can process a very complex information. So they are intelligent, but they don't have technology because they don't need it. And I think that's something we really need to focus on, is how an evolution of an intelligent species will lead to technology. And finally, the big unknown parameter here is the length, or the length of time, the duration of this technological civilization. And that's we don't know. We don't know again because we have one system. We can suspect that this number may be low. And you can see that by simply looking at our own civilization. Humanoid has been on this planet for 2 million years. We had civilization like Mesopotamian civilization that went and disappeared. We have also some of them here in United States that grow, like the Maya, the Inca, and others, and then collapse completely. So it seems that the civilization has a duration which could be between 400 to 1,000 years. So maybe that's also a strong limit here, because it implies that if two civilizations in the galaxy wants to communicate, they need to be intelligence and they need to be there at the same time, and the distance are so huge that it's a very unlikely. But there is so many stars and so many worlds that it may happen, and that's the question we are trying to understand. Sorry, I was way too long on this equation.
No, it's great.
It's the foundation of SETI, basically.
It really is. Yeah. Can you tell us a little bit, one of the things that I think is really fascinating about the EV-scope and our network is that it's not just a device to observe the cosmos, but we get to work with astronomers, real astronomers, and the scientists at SETI to work on portions of this Drake equation and to learn more about the opportunities for life beyond our own Earth. So I'm curious if you could tell us a little bit more about the work that citizen astronomers through Unistellar's network have done in partnership with SETI and the professional astronomers who work with you.
Yeah, so we started this program very recently. I mean, that was in the concept of the telescope to be able to allow people to do scientific investigation, but we frankly started that in 2020. As you know, we have now 3,000 telescopes available on this planet, people willing to observe. And what we're trying to do is to harvest this energy, this interest in astronomy, by giving them the opportunity to do observations that could be interesting for scientists like myself and others. So you met those scientists, you met Dan, Tom, Val, there is more, of course. So we are, each of us have basically conducted some kind of some scientific project, and we send alerts to our network, and we kind of encourage people to participate to those observations. And here you have a picture of our citizen astronomers. Those are backyard astronomers who basically dedicated hours, sometimes nights, sometimes they observe way more than us, in fact, to observe the dark sky and to conduct those observations. So I'm going to give you a few examples of what have been done, but there is way more than that. So this is a very interesting case. It's a transiting exoplanet. So Tom mentioned this. Now we can observe planets orbiting around stars, not directly the planet, but by seeing the shadow of the planet. So what you can see, if you look at the stars, you can see a small attenuation of the brightness. And that's the red line you see here, because a planet is passing between us and its star. So with the EV scope, you can detect in your backyard a Jupiter-sized exoplanet transiting a sun-like star. And I think this is remarkable that now we have the technology to do these kind of things. We have been observing multiple of them. I think we have around 20 transiting exoplanets so far.
So when people utilize their EV scope, we've seen some of the images and what it looks like to observe the objects. Is this what the data looks like behind those images? Is this what the scientists at SETI receive?
Yeah, so what we do at SETI, when an observer does this observation, he can send us the observations. So we collect them on our server, we detect them automatically now, and we are capable of processing the data relatively quickly. In fact, we're improving this to the point that we think it's going to be possible to do that in 1 hour. And then we send the data, the result to the observer. This is we are working on this pipeline. Of course, it's not as easy as expected, but we are making so much progress that we went from weeks for the data process to a few hours, and for the transit, that's what's going to happen. So in a few hours later, you receive on your email or soon a user account the profile of the observation, and we will be able to collect all these observations together for all the network to be able to refine the transit itself. So its profile, but also be able to measure exactly the timing of the transit. The more telescope we have, the more accurate will be the measurement of the timing of the transit. And I know you're all fascinated and you want to know why we care about that. Well, it's because measuring the timing of the transit exactly, we may be able to detect the presence of forces that are not gravitational directly. So there could be, for instance, forces directly due to the presence of other planets in orbit also around the star. And those other planets are affecting basically the orbit of this one. So that will be an indirect way to detect another planet in the system. We can also detect rings maybe around this planet by looking at this profile with multiple telescopes.
So beyond exoplanet transits, another major initiative that you've been working on between Unistellar and SETI are asteroid occultations. Please help us understand what that means and what this has to do with the search for intelligent life.
Yeah, so in this case, we are interested in our solar system. So as you know, there is more than 1 million asteroids in our which has been detected in our solar system, and we think there is more than 20 million of them. Okay, and some of those asteroids are particularly interesting because they come very close to us. We call them near-Earth asteroids. They're interesting because they come close to us, so we can better study them, but also because they could have an impact. They could impact our own planet. So as part of the Planetary Defense Program, which is a official name for this kind of program, which consists in analyzing, mitigating the potential hazardous asteroids, we have now monitoring the sky with the EVScope network. So if you have a EVScope user, you will receive on a regular basis the possibility of participating to campaigns like that. So we had multiple flybys. So those are tiny telescopes, like 10 meters, like the size of a house or a castle, to give you an idea, who are passing nearby Earth. And we observe them with multiple stations. And from this, we refine the orbit of the asteroid. So we'll be able to know whether or not it will impact Earth in a few days, or in a few years, or in a century, or never. And then, what you just showed before, this is a more complex analysis, and that's the first time we did that with the EVScope. It's basically the shape of an asteroid which has been built based on multiple observations from EVScope users. We have, in this case, 28 observers or 30 observers, citizen astronomers, who collected data for 2 months, and they were located in 7 different countries. And we gather all these observations. We get what we call the Lie curve, which is, let me show you that. An asteroid is not perfectly spherical. It generally has this weird potato shape. So when it spins on itself, like that, and moves close to us, there is a variation of light. And this variation of light is related to the shape of the asteroid. So my colleagues at Charles University in Prague developed a very complex algorithm for which you can go from the shape, the Lie curve, we call that, to the shape model. It's called inversion method. And we use this algorithm to develop the shape of 1999 AP10, which is a 1.6 kilometer asteroid, near-Earth asteroid, one of the largest in the largest NEAs in this population.
And I'm excited to talk about NEA 1999 AP10. Quite a long name, clearly needs a much catchier new name. But it's really fascinating because what you did isn't just unique, but it's only been done 68 times prior in history. And so I think it's fascinating that this now 69th time was something that was done by backyard astronomers, people who were using the EVScope in cities and not necessarily using the very large telescopes in more remote locations.
Yeah, that's something I didn't mention, is that what we're doing with the EVScope and its network is basically scientific studies that was done before by professional astronomers 5-10 years ago. This Lie curve inversion technique is relatively new. It's not something that was developed a century ago. We just learned to do that. So with this technology, with this EVScope and the quality of the sensor and the fact that it can be used by everybody can become a citizen astronomer, and everybody can participate to this program. I mean, it's true there is a learning curve for science. It's always the case. But I think that's the most fascinating part of it, is that any of our citizen astronomers, they are different type of people. Some of them are scientists, some of them are artists, some of them are people who work in coffee shop, etc. It's amazing. Every morning I talk to some of them because I send pictures, and I think it's refreshing to see that we're giving access to science to these people.
Well, that is a wonderful time for me to introduce the winner of our Nickname the Asteroid contest. And so this contest we launched in early December to celebrate this incredible achievement between the Unistellar and SETI teams. And we never could have imagined how appropriate the winning name would be. And so with that, I bring to you the winner of our Nickname the Asteroid contest.
Astronomers with Unistellar and SETI hope near-Earth asteroid lovers across the world.
So I want to turn it over to you to say a few words about Ada Carrera, just in case there were any sound issues. She was the overwhelming winner of our Nickname the Asteroid contest. She's a legendary female motorcyclist who, for the last 40 years of her life, was a huge advocate for astronomy education for the people of Mexico. She was also an incredible female powerhouse. She was the first girl to speak to the first Mexican girl to speak to the United Nations. She had such a passion for life, and her son Alvaro championed a campaign to have Ada's name attached to this near-Earth asteroid, and it makes a lot of sense. I mean, she was a very fast-moving powerhouse of a woman who had such a passion for space and astronomy and founded a number of different organizations throughout her life to bring astronomy education to Mexico. And it's just amazing when I say she was the overwhelming winner. Not only did she receive 60% of all of the votes from this contest, but her community submitted her name so many times that she received 15% of all submissions to the contest and made up the vast majority of the top 30 vote getters by vote. So huge congratulations. Frank, anything you want to say about Ada or to her community?
So I personally think it's amazing that we are we have as a community to find a name for this asteroid. It's really part of the activity as a scientist to discover things, but also to name them. We do that on a regular basis. When we take first picture of a body, we name the features, and then we generally nickname them. So this is really truly being part of the scientific process. So I personally think this is great, and the name is great as well, because I did not meet Ada when I was in Mexico, but I heard about her from other people. She had this passion for astronomy. She created so many astronomer club that I think she's legendary over there. And she has this passion for astronomy, which was also not only for astronomy, but for like the concept of giving the sky back to the people and giving them the opportunity to see through telescopes and to enjoy the dark sky and to meet scientists and to talk to scientists and to also go together to see an event like the Grand Conjunction we have now.
Well, thank you. I am so excited to be able to let the news out. I just want to leave everyone with one final observation that you captured just moments ago. What are we looking at right now?
So we're looking at M33. So this is in my garden. I'm just like, right now while I was talking to you, I decided to launch an integration. So that's why it took 46 minutes. And this is a galaxy which is 3 million light years away from us. It's one of the most beautiful we can see at the moment at the beginning of the night. It's part of what our local cluster of galaxies. Okay, we have the Milky Way, and we have Andromeda, and we have this one and others. So they're very like close-ish from each other, 3 million light years away from us. It means that when this light left this galaxy to reach us, it was just when basically we had the Australopithec on our planet roaming around. That was just the beginning of humanity, as we know it. And this is a galaxy which has a spiral arms like ours. It's smaller. It's 40,000 light years in diameter, and there is only 45 billion stars in it. But every time I look at this galaxy and I think about it, I think about the fact that somewhere here, maybe in this galaxy, there is someone else using something like an EV scope, looking at us as well, and looking at the spiral arms of our galaxy and wondering whether or not we are alone. And that's, I think, the most inspiring moment in astronomy, when you see with your naked eyes something so far away, so distant, and you realize the gigantism of the universe. And you are mute again, Whitney.
I can't think of any better parting words, so good that I had to mute myself, than, looking up in the sky. What a reassurance that although we're all socially distant right now, we really, truly are not alone. And let us hope that there's someone out there peeking in on us, looking at our own Milky Way galaxy this evening as we look out at them. So thank you to everyone who joined us this evening. Thank you so much, Frank. Thank you to all of those EVscope users around the world who submitted their images. We hope you had a wonderful time during our Winter Solstice virtual star party. Until we see you again, I wish you all clear skies.